Hello and welcome to my talk about tremors and shaking up the real-time stack, the patterns and pieces I'm replacing with tremors. So a quick warning ahead of time, as with any talk I do, I have to give you this because most of these puns are intentional, but some are just terrible and I might have not even seen them when I started. So if it gets bad, remember, you were warned. So, let's start with a quick agenda. First, I'm going to tell you who I am, what I do, and who for. I'm going to set the stage for what I'm talking about, tell you a quick story, explain the issue in more detail, and then hopefully walk you through some architecture around why this is a cool solution to that problem. As this is a recorded talk, questions and such will be done a bit asynchronously, but you can always find me in the Discord afterwards. So, quick thing ahead of time. Let's talk about characterization. Now, this is nature's kind of habit of trying to evolve the crab over and over again. At various points in nature, all kinds of various creatures have turned into crabs. And the reason I'm bringing this up is, until relatively recently, I used to work at a company called Ably Realtime, a massive pub sub networking broker which could do WebSockets at any scale. However, over time, I evolved into a crab. And these days I work at Ivan as a developer relations manager, doing slightly different things to what I used to do. So to this end, a lot of those slides still have Ably written on them because, quite honestly, I like the slide template a lot, and I kept it because it was what I had. So let's talk about me. These days, I work as a bit of a tech sommelier. My job is to pair you some Kafka over here, a database over there, and maybe a nice piece of cheese in the middle. We don't get wine these days at work, but hey, we could always hope. I've worked on everything from MMO games to massively multiplayer simulations to medical devices and military technologies. I've basically been the go-to guy around the edges of things, bringing that kind of R&D spirit and the art of the possible to light. And these days they pay me to make silly demos and terrible jokes. Fun fact, I've actually written production Pascal in the last 12 months, in fact, not even 18 months, due to someone needing some really old systems to talk MQTT. And these days I code in Rust as much as I can so I can make more crustacean jokes with Ferris and Rafu, who is the Ivan crab. So, without further ado, let's talk about real-time. What is real-time? Okay, so the thing about real-time is it's kind of like has many definitions. So it's often about bounded latency. So the idea of, we know when a message will arrive or a thing will happen within quite a tight time limit. Particularly in hardware, this is a big thing. You often hear this term of a real-time clock or kind of a hardware watchdog that means real-time is actually a bounded thing. Often it's used to refer to low latency. This is where Ably used to call it, which is the idea of saying anything under 200 milliseconds end to end is what's referred to as a blink of an eye, and it's very hard to tell. In games, this would be 16 milliseconds on a good day, and on a bad day, you're looking at 8 to 2. So you get this thing where it's like low latency is another one of those soft metrics. You're never quite sure what people really mean by that. And then, like in other cases, we mean things like micro-batching. When the crowd at Apache Spark and Databricks with them start talking about real-time, they just mean micro-batches, which is rather than waiting all day and then converting, they mean every few minutes they're converting. And for a lot of use cases, this is as close to real-time as they need to get, or what they define as real-time. Now, the next kind of thing, which is the most obvious change here, is streaming. Now, streaming, of course, is the idea of just continuously changing data rather than batching data. Now, one could argue that just means your batch size is now 1, and others would say that is being facetious. I am often facetious. So I can simply say that it is part of the story. But the real thing here is, as with everything in software, it depends. Now, this is because it really depends what your outcome you're looking for is. In hardware, real-time actually has a very distinct meaning. In software, it nearly always is as soft as it is hard in hardware. Now, whether or not the irony of the words there actually mean anything, but in software, real-time, and particularly soft real-time, is mostly just about getting things done as fast as possible with the most bounded set of latencies. This is where those kind of P99s and P99.9s start coming in, of saying, we want this thing to finish within a known context so we can act upon it. So the thing is, you kind of look at what real-time is and you think, what does it do? It's things like chat. This is the ability to send messages back and forwards between people, right? we're going to be talking mostly about a messaging context in this whole setup. It's also things like stock updates. This is continuous streams of data which can go down to the nanosecond level accuracy in some places. But in general, over the web, it's still hundreds of mils, and trying to get those things as fast as possible to the users with as little latency as possible. And then, of course, like map updates. This is knowing where someone is, or your bus, or your Uber. And this kind of data needs to flow around, otherwise it stops being relevant. It's all well and good to know where your bus was, but we've all been there. It doesn't actually get you what you need. And the kind of real thing about real time these days is it's getting everywhere. Once you start making things faster, no one's very much willing to make them be slower again for nearly any reason. Once your web pages took under a second to load, you were very unwilling to go back. It's like saying, would you like some 56K modems, or do you fancy not having Wi-Fi anymore? And the short answer is no. No one is willing to go back. And because of that, it's hard to do, right? And this is the other thing, is you're definitely becoming doable because we've got this everywhere. And it's actually not the full story, because uptime is not exactly easy to guarantee. And because we've already had that established fact of no one's willing to go back, right? You've got the fact that, like, once you have real-time bets in, let's say it's the Super Bowl, if it breaks, everyone gets very upset. This is what happened to Canby last year in the Super Bowl. Suddenly they were taking many, many more bets, and something happened, and they crunched, and they lost lots of their customers. This was not good. In a recent online game launched by Amazon of all people, so with all of the AWS behind them, they were still having queues of players into the days because they couldn't handle the real-time load. And we've all seen Slack die repeatedly, because it does. And this is because real-time is hard. And it doesn't mean it's not always up, but it does mean it does go down. And that's the thing, because, you might be wondering, why is this even a problem? And, outside of a bit of a user experience thing, right, it's only going to be more of this. So we've already got a problem. We already know the way to solve loads of things people want is real-time. And now we know that real-time is unreliable, at least currently. And there's only going to be more of it, which is why it gets even more complicated. So if you think that, 5% of the data is real-time today, and it's heading towards 30% by 2025. That was the previous estimate. The current estimates are now about 40%. If you think about that, this is in an exponentially increasing data world. So 40% of triple the data right now will be real-time. And we've now got to start thinking about how we handle that. And this is where it gets even worse, is data requirements are not distributed evenly, right? Everything wants different data. Everything wants data differently. And not everything wants all the data. So you have this simple problem of lots of data is flowing around the system, and an uneven breakdown of user interest and system interest means that you have to have some way of sorting data out. Now, let's get to that story, because I've set the stage. Now, this is mostly about some context about why this is a problem in a real-world scenario. So let's talk about the FinTech application. Now, this is just the front page of the Google Play Store of FinTech. You can go through about 3 more pages of these, and each of these have hundreds of thousands of users, and they're all streaming FinTech data around the place. And let's say you have one of these apps, and you want your users to get updates. Of course, these are people who want to know what their current balance is, what their current stocks are worth, what stocks are worth so they can buy them, and what those lovely crypto coins can do for them today. And of course, they all want to win. And the problem here is that, the perception of speed matters. This is where they don't want to be seen to lose because the things aren't happening for them, because users are not very forgiving. And of course, this little Simpsons clip tells the story of someone getting out-of-date data by a factor of 80 years by missing the big stock market crash in the 20s. But of course, this actually happens quite regularly. People often lose money because they can't get an update through. They don't have a system which has the uptime requirements or the guarantees of message delivery. Of course, these things, you always work on them, but the problem ends up being that, unless you've designed from day one to have this, you have a problem. So let's talk about the architecture that powers systems like this. And this is where we start to generalize out. The FinTech app is a great kind of starting example, because there are real-time stock feeds going everywhere. There's tons and tons of systems behind the scenes. But if we zoom in to see what's going on, we have all these microservices, right? You have thousands of bits. Some of these are for fulfillment, some of these are for order tracking, some of these are just for user tracking, some of these are for logging the services which are also there, and some of them are for logging those. And as you build up these various pieces in a modern system, you end up with this microservice swarm, with data moving steadily around to various people. And we do this because, of course, we don't have a homogeneous network anymore. We have a heterogeneous system with many different people at one end and many different systems and services at the other, and different requests require different pieces to fulfill. So we have data moving everywhere. Now, with all that, we end up needing a layer to plug it all together. And this is where we start having to talk about PubSub. And I don't mean nautical-themed drinking establishments, but instead I mean a way to have a strong pattern between consumers, producers, and the systems in between them all. Now, these are the kind of classical pub subsystems you'll see these days. We have Kafka, which is the canonical example to database concurrency being used as a way to share data. We have RabbitMQ, showing that you never really need to go beyond version 0.9 to succeed. NATS is a perfect example of why you can just rewrite your software over and over again in different languages and still somehow succeed. And of course RabbitMQ, showing that every now and again you still just have to buy legacy IBM tech because it will just work. MQTT is a big area of interest for me, but a little bit different from the others. So in this case, we're going to think about the most popular answer, which of course is Kafka. A Kafka cluster, or clusters, can allow you to do all this kind of stuff behind the scenes in your network. It gives you this kind of loose coupling between services because you publish data onto a Kafka topic, n number of systems can read it, and it doesn't really matter if the systems die because Kafka is actually a storage layer. You get some strong guarantees because you can actually say some very good facts about Kafka. You can put more access into the system. It is a distributed and fault-tolerant system by default. It tends to be a lot more reliable than the microservices on top of it. And in general, you'll find that end-to-end latency decreases because you no longer have these systems coupled with each other for values. They're no longer fighting because Kafka can have multiple readers, assuming you set it up right. However, this isn't quite the full story. As you now build these fire hoses of data, Kafka topics can take a lot of data, and the more partitions, the more data. But of course, it's all there in immutable, arbitrarily structured logs. Kafka is byte-oriented. Though you can have schemas for records, there is no strict requirement. And you now have this data flowing between any number of heterogeneous systems. And this is once again back to that previous microservice web, where you do not necessarily know what's going to read from a topic, though there are controls, but you do not know what someone else will want to read from that topic. And there might be data in there they don't need. And because it's in an immutable log, you've got to read through it all. You can't really scrub and say, give me X. There are no predicates, no filters. You can say time, or you can say offset. And the thing about this is where it's difficult is each of these systems has a finite bandwidth, even inside your network. And this makes things heavy and expensive because you're going to start eating bandwidth up on things that you don't need because there's a lot of data around. Particularly with Kafka getting very large and lots of systems there, is you have rich data. That's great, but you didn't want it all. And unimportant events are going to start doing the whole head of line blocking thing for important ones. Or just the insight you need, because you now have 30 events that are just saying normal, 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 and one saying, oh no, panic. And you don't necessarily want the alert system to have to read all of the normal, normal, normals. You just want it to see the important bit. So let's talk about connecting to Kafka, because now we've got a Kafka system. We're not just going to be using standard producers and consumers, because that's a lot of work, and also it's a lot of extra programming burden. So what we really want to be able to do is have X systems that pull Y events from Z streams, right? These things cross over all the time, as you've seen on the big web. And the idea really is you need to express the interest of a system as a subscription to a series of topics. And classically, you just query for all this, but you don't really want to build like REST APIs or anything other than a real-time API, because once again, you're back to hello, yes, good. And this is why things like gRPC fail as well, is though you can multiplex up streams of data, these are lots and lots of point-to-point communication methods. And we really just want something simple but robust in the middle. And this is where we get to the challenge, which is that all data is not equal, and it's not equal to any player. Every single system, every single user would like a different subset of the data. We can't stop the world, which means that, everything must continue. If something breaks, it has to just fail on its own. It means it has to be fully decoupled. Things can't just cost endless amounts. If we could just throw all the data at all the things and just have unlimited compute, that'd be great, but we don't. We can't, and increasingly that's proving to be a very ungreen solution, along with just an untenable solution. Bezos would be very happy with us if we just kept spending more. There's also a very important need to define what is important and have it dynamic. So this is the ability to say, this data is relevant for this system, this data is not relevant for this system. This is an alert, this is worthy of actually triggering something, this is not. And be able to discard things, because a lot of the time we're storing all this information, and if it's unimportant, we probably shouldn't be storing it, or we should be aggregating it before we do, because disks is actually a finite thing. And the last but and most important thing is we're working on events. These are event-driven systems where you want a subset of events. We're not working on tables of data we can just go and query with a predicate. It doesn't exist in most cases. So what ends up happening is, rather than just going, give me X from the database, give me all important events, and then doing a query over it, we kind of need to decide on a per event basis. So what options do we have? So obviously everyone's going to have heard of Kafka Connect. Kafka Connect is another distributed system which uses a bunch of the Kafka protocols to run on top of or next to Kafka as a separate distributed system, which allows you to pull things in and out of Kafka. It's very useful for putting data into Kafka because, of course, that's what it's really been designed for. It can pull sources, it can pull from things, and it allows you to have transformations, converters, and schema tools attached. So often you might do some change data capture out of something, let's say like a Postgres server, using a tool called Debezium, which is a Kafka connector, and it will get the changes of that from that write-ahead log in your database into your Kafka topics, so that you can then act upon them accordingly. It's a great way of turning transactional data into event data. Other sources, of course, mean you can poll, URLs or anything else, or just pull in from whatever else you want. This is a very powerful pattern, and then when you flip it around, it allows you to push data to places. But when you start flipping it around, you end up with the problem of it's another distributed system. It is independent of Kafka by sort of design and has some interesting problems, such as it doesn't have back pressure in the sink, which means if the Kafka starts to back up, you don't have any recourse but to keep going. Now in Kafka, that's kind of to be expected, as it's a full-on disk log, so you can just keep going. But because of the nature of it right now, and it's been subtly neglected, in my opinion, by the community behind Kafka, is that it's not as robust as it should be. If sync tasks start failing for the wrong reasons, you will just start bringing down your cluster. And also, because it acts per message, it doesn't have any kind of aggregation capabilities. It is, of course, a tool you can just build upon, as it's really an API, but that does end up meaning that your options are to build a lot of functionality yourself, or rely on the fact that it is relatively limited in what it does. Personally, I find that this is a great in and out of your system, but nothing else. It doesn't really let you do much more. The transformations and tooling you can put there are best used to simply mask data out, convert some fields, or just normalize. It's nothing more than that. And because of what everyone in the ecosystem seems to expect, it kind of requires more schema knowledge up front. So the next, of course, pattern is Apache Camel. Now, this follows what's known as the Enterprise Integration Pattern. It's another Apache product, because lots of things are, and it's sort of the idea from yesteryear of saying, I need a way to basically be message-oriented and to be able to convert between various messaging systems. It's actually a surprisingly well-supported project, and Red Hat even has a hosted variant of it, but really it's just mostly JVM libraries. Now, these are really powerful, once again, for just getting stuff done, but the big downside of, once again, is it's JVM only. Now, that doesn't mean it can't talk to tools, but it does mean your outputs are now the JVM. And if you're out of the JVM, you're in a bit of a bad place. Pardon me. In addition to that, you run into the simple fact of these are going to limit what you can do, because these are really about getting your data into code. And that's great, but you might want to be able to do some stuff outside of having to deploy a separate service. So what about Apache NiFi? Now, Apache NiFi deserves a little bit of interest from mostly because of where its origin. It is the tool with the most shades of grey I've ever seen in it, which is kind of ironic considering the NSA are the ones who built it and open sourced it. It's an actual kind of like live ETL data gathering type solution, where it allows you to have this kind of low-ish code setup, which allows you to pull data from various sources and put it to various syncs with various rules in between. It's very powerful for building up a kind of network of systems which pull data and move it around. However, this is not kind of free. First things first, it's another big, heavy distributed system. It has quite intense memory and compute requirements, which is quite surprising considering what it does. And it's also not hugely supported, and with quite a small community behind it. So the thing is, it does do most of what kind of I'm after here and what most people want, but once again, like, because of that kind of smallish community, the lack of knowledge behind it, it's very hard to kind of put it into scaled production. In addition, its actual transformation tools are less powerful than most would like to admit, and what it really serves to be is the Kafka Connect of everything, more than it serves to be that kind of real kind of transformation-y tool you want. So then, of course, we come to the most powerful tool I'm going to go into here, which is Apache Flink. So Apache Flink, it came out of the kind of thinking between Apache Storm was quite fast, but really unreliable, and Apache Spark was very reliable and could crunch a lot of data, but really quite slow and batchy. It was just Hadoop done right. Now, this is where we come to Flink, which is the idea of how can we have a bit of both worlds of quite fast or really fast, and heavy compute with all the guarantees we'd want. Now, Flink increasingly is sort of looking like that, not quite panacea, but very powerful tool that can solve lots of your semi-real-time problems. With a lot of new companies springing up around it, as Verica has sort of fallen by the wayside, the interesting folks have gone to Immerok. And of course, the other side is Decodable. Now, these are real-time integration platforms that allow you to both either write code or just write SQL to sort of integrate the stuff. I have quite an interest in this because, of course, where I work, we also have Apache Flink, the SQL variant, as a way to integrate into other data sources. Flink has a lot of added bonuses, but it is also just a very large-scale compute engine, which allows you to write code that runs on distributed systems with hard guarantees. It has storage layers built in, and of course the SQL layer hinted at earlier. Now, Apache Flink SQL, to be honest, could serve a lot of these purposes. And this is where Decodable would say, this is perfect, just use Flink. And you can do all the enterprise integration patterns you want with it. You can merge the data, sort the data, whatever else the data. And this is where it starts to fall down a bit, is it's still SQL. As we're not just maneuvering data from place to place, and we're not just filtering it, sorting it, or anything else, we often need a little bit more than what SQL offers. But also because Flink is another JVM thing. It's huge, it's powerful, but the SQL system is limited by whatever else you've added. To go beyond that, you're into actually writing code again, and hopefully making sure what your current Flink job is as powerful as it needs to be. Now, I'm not saying Flink is bad, but it's also just one more tool. So then, like, what about Tremors? Kind of the reason we're here, shall we say. Now, what I like about Tremors, and here's why Tremors, I think, is it's new. The first big thing here is that, what does new bring you is cloud native. Now, cloud native is a big deal because every single other system I've previously talked about kind of predates, in a lot of ways, that kind of full-on containerized thinking and that evolution we've had when it comes to running big systems in the cloud or on any hardware we want. Tremors was designed from day one to be running in Kubernetes, running on N systems or in clouds, and just to be out there and deployable and manageable with these kind of thinking in mind. It's also got no JVM. Now, you may have heard me complain about the JVM a little bit. Now, don't get me wrong, the JVM is a piece of powerful magic, and it genuinely does an awesome job, but stop the world garbage collection is a thing, and however you fight it, you will eventually run into running out of heap memory and not knowing what's going on. this is where GC pauses become a problem, but more often than not, it means if you start memory leaking, you do not know how to stop memory leaking. There are people who can do some amazing things about no GC Java and can claim to make this thing just work. However, that's not me. The other thing here is that, in a very real way, I don't want to have JVM processes running all over my stack. JVM is great until it pervades everything you do, which is why camel is kind of a no-no in my world, is I don't want everything to be in the JVM. I want things to talk APIs, not languages. The next thing here is no hard schemas. Kind of Tremors right now is kind of message pack all the way through and doesn't really enforce things, which is kind of really useful. Most of the other tools expect some level of schema in the data. This is where kind of the SQL approach, in my opinion, falls down badly, because it requires you to know a lot more about your data. You can't say expect X and hope, which is what you often want. I've dealt with so much, should we simply say, unstructured data in the past that not being able to just introspect it and act is a real issue. Whereas having a SQL engine is really powerful, I can't guarantee it's going to work. And I can't guarantee I can explore the data and change it very easily. The next thing here is this kind of statement-oriented DSL, which is kind of the replacement to schema. This is the ability to express your desires as a series of things, which is not Turing complete, which means you can't have people doing some truly naughty things. Don't get me wrong, you can do some stuff which is very silly, but it's designed in such a way to limit the kind of transformations you do to a sensible subset. And this is really powerful, and although it's something new to learn, it's not huge, and it kind of works for what it seems to be set out for. And here's the big one for me: it's designed with JSON in mind, right? Like the world, however else we want to say right now, is JSON has won. XML is dead for good and bad reasons, and most other systems are just a way of making JSON better to transfer. Protobufs and everything else, really, and Avro and all the rest of it, really, we'd send JSON if it wasn't so big and bulky and annoying. But with things like message pack and a few of the others, fundamentally, the data is just a series of key value pairs, which we want to be able to sort through and act upon. And it can be nested deep, and this kind of thought thinking up front is what really makes a kind of big change, in my opinion, to why to use Tremors versus other things. We're not dealing with rows of a database anymore. That's just not what we're doing. And because of that, it's like this kind of backwards retrofit of SQL to work on JSON, or even JSON buff, to be honest, just doesn't really make sense from a get-go. And last, but very much not least, it's actually open source. Now, every tool I've mentioned previously is a full-on Apache project, pretty much. And the only reason I've not talked about anything else is because they are not. I'm not really interested in looking at a tool right now which has a business source license or a server-side public license attached, because fundamentally it's not even that I think I will actually host it myself and make people pay for it. That's not the problem. It's that I need to know that there will be more than one company being an upstream committer, and this is the important part of any evolution of any project, is having multiple people interested in it so the development can go faster. So let's talk about my requirements. Now, as I previously mentioned, I work in developer relations, and what this normally means is my job involves touching millions of systems in all different ways and making them work. So I need tools that simplify my setups. They allow me to rapidly experiment with things, they scale out the box, they've got to be performant and extensible and open source. Where I work at Ivan, every tool we have is open source, everything we build we nearly always open source, and by open source I mean Apache 2 or better. And it's kind of a core mantra. Therefore, if I use a tool to demonstrate something which is not open, I'm going to have questions because it doesn't fit our culture, it doesn't fit our way of working. In addition, I use Tremors for all the personal projects around simulation. And the key thing here is this kind of rapidly extensibility of it. There's a very good framework and APIs in Tremors to just build more stuff. Also, it just supports UDP out the box. And this is the first tool I've got to use in this data space that I could just throw UDP at and it would work, which made me so happy. So let's kind of dig into two of those things. And keeping the hot path clear is a huge thing. Tremors out the box has all the circuit breaker things kind of thought out on day one, and it's designed not to block when it doesn't have to, which means that you don't end up with these kind of, you see those hot lines there, those should be fine. It's not about, a lot of this happens in so many systems, right, where you end up with, particularly in Kafka, because Kafka is the kind of backing thing I'll be using for most of my work, is you end up with these topics that start having offsets growing and consumer groups which are just going, sorry, I can't. And then what happens is down your kind of graph of data, you end up with something blocked because of a couple of bad records happened at the same time. This is where, like, you know, there's a lot of patterns you need to be able to support here. The kind of, error, log it, move on. Or circuit break out of that bad state and move on. And a lot of tools don't really have that baked in. Kafka Connect is famously bad at this. It even has like dead letter queues built in, which most people don't know about. But that's not good enough. You kind of need it to have it thought out from day one. And of course, we got to manage connectivity. And this is the kind of big one for me, right? Because, like, you know, right now at Ivan, we have 11 products. My video face is on top of some of them right now. But the key thing here is that these include databases such as ClickHouse, Cassandra, OpenSearch, Postgres, and MySQL. And we have also M3 and a few others. And combine that with all this stuff, and suddenly what happens is you have a recipe for requiring millions of connectivities. But when you combine that with, let's say, you know, GCP's setup, you have even more. So we went from 11 products to 20-something in one click. And then, of course, we have to remember that we also have AWS there with their 100 and something products of their own. And so, you know, we have hundreds and hundreds of things that talk. A lot of them talk the same language, but it's not really enough because, you know, I don't want to have to write custom HTTP connectors out of Kafka. I want a tool where I can just write a DSL and go, right? A lot of these things speak HTTP, which is great, and Tremors does as well. And they also most of them speak Kafka, and Tremors does as well. But because of this kind of DSL for filtering, merging, and changing and aggregating data, I can make sure that the outputs I'm looking for meet these requirements. Because this is actually a real problem when you start looking into trying to build one of these big webs. And for me, winning ends up being having fewer middleware systems. And with Tremors right now, I've gone from requiring a ton of tiny little microservices here and there that do the one-off conversion, nearly always a quick Python box or an AWS Lambda, to just being able to write a short bit of Tremor script and just having that in my Tremors cluster doing the job for me. Going forwards, I can't really see me not doing this everywhere because it seems like a clear win. And this is kind of where I kind of come up with this point of where what Tremors really replaces for me, in addition to all those kind of tools previously mentioned, in the biggest way, it replaces those annoying tiny microservices you end up building. The 35 lines of Python, the files processor, the stream processor, the AWS Lambda, because they aren't reliable, they aren't scalable, and instead you just want a system that does it. So, thank you for listening. Please ask questions either here or in the Discord.